Hi, welcome back. In today's video, we're going to be having a look at focal search, which is a very interesting algorithm and essentially is useful in two primary contexts. So first, on its own, we're going to be essentially weaving in the idea that focal search is going to optimize a secondary objective at the same time within our A* framework. So what that means is we might care about something else in our problem. So for example, I study pipe routing. Perhaps I care about actually trying to not only get the exact optimal path, but try to get one that is also minimizing the number of bends. Something like this, right? You can weave in this additional function however you want to represent something you care about in the problem. Focal search is going to be this balance between returning a bounded suboptimal solution, something that we're okay with, right? We have control over how bad we allow the solution to be. But within that space, we're kind of also abusing the fact that we're okay with this little subset over here of suboptimal solutions. And we're going to then prioritize optimizing by a secondary objective. So focal search in that context is interesting in its own right. But I also want to point out that the reason kind of we're introducing this idea is because focal search, when paired with multi-agent pathfinding algorithms, specifically for now, conflict-based search CBS. Together, using both focal search for both the high level and the low level of CBS, well, we're able to get something that is called Enhanced CBS, which is a very exciting and performative algorithm in the literature that takes CBS from something that really was unable to scale beyond even like 10 agents to something that can go much farther beyond. And it's essentially birthed an entire family of algorithms. It's not just ECBS, Enhanced CBS. The acronyms continue for a very long time because people have been building upon these ideas because they are very exciting and performative. So that is why focal search is important. It's going to enable this other ECBS avenue as well, but it's also, I think, just interesting in its own right for this idea of kind of somewhat optimizing both objectives at the same time. Note, right, this is very distinct from the idea of bi-objective search, where you are actually trying to optimize directly two different objectives, right? Two different criteria for what you care about in a problem. That is an entire field of study in its own right. It's very difficult, it's a very difficult problem, and I will have videos on that in the future as well. But you have these additional concepts of this massive Pareto frontier, and essentially the problem is not easy. Focal search is easy because what we're doing is we're just happily accepting bounded suboptimality, and then we abuse that little bit of information to prioritize things. So let's have a look then at what this even means. So in focal search, our frontier now is not going to be represented by just the open list. We're going to be using two lists instead. So, well, I mean, I just said it though. The first one is that open does still exist, and it is sorted by the same thing that we expect always. We're going to be calling it F1 of n now though. And this is our age-old A* G of n plus H of n. Okay, so nothing's changed. Open is still sorted by our A*, our strict admissibility, right? So maybe I can label this as strict admissibility. Yeah, just as we expect, this will give us optimal solutions if we expand by this. But now what we're introducing as well is within open. So we're going to create something called the focal list. The focal list is going to be a subset of open that's enabling us to do this little prioritization. So focal is a subset of open and is sorted by some other function, F2 of n. Okay, we're going to have to pick that one. So we'll talk about that later. But the really interesting part of F2 is actually this can be possibly inadmissible. And it doesn't matter. That's actually quite nice, right? Because we're still guaranteeing bounded suboptimal solutions, right? According to this nice A* behavior of admissibility and everything that we know from A*. But we're able to just come up with any other function we want, and we don't even have to care about things like admissibility. You don't have to go and spend the time to try to see, well, is my function consistent? Is it admissible? so forth, which often usually excludes a lot of things that you as a human being might just actually want to care about very easily. So such things as, well, I already mentioned, right, the number of bends perhaps if you're doing pipe routing. So that is kind of where we're getting at focal search, but I have to talk about what even is focal, right? Where is focal? So what we're going to be doing is we're tracking two things now. So you track in open what is the smallest, the minimum f value in open, right? This is obviously going to be the f value of your first node because this is the most promising, right? This is what is ranked next in terms of your standard A-star expansions. Now, we're talking about this idea of bounded suboptimality, right? So W bounded suboptimality is kind of where we're entering into this equation. And what that means is at some point in time, somewhere else down the list, we have this cutoff of what we were happy with trading, right? At some other point in time, we know that there also exists essentially a window size, right? This window size is the size of our W suboptimality, our bounded suboptimality. We define some form of W, you get to choose this and parameterize this based on how much suboptimality you're okay with. 2 times more, 10 times more, whatever else, 1.5 times more. However, this defines essentially a window here of nodes that we're saying within this guarantee, we're okay with any solution that is at least this good, right? Well, what that means is we're going to essentially define a new list over here, focal. Focal is going to be simply taking essentially this little part of our search tree here. While this is being transformed, these nodes are being taken either based on your implementation, right? Either out of open and put into focal, or you're defining focal as like an actual explicit subset of open. However you implement it, it doesn't matter. We take these 4 nodes that appear in focal right now, and we rank them according to F2, according to our other metric, our other objective that we want to try to optimize. So this could look like anything, right? It could be BA, DC, how about that? These nodes are ranked according to some other criteria, and we will expand nodes in the order of focal, right? And then that is essentially when we pop it, right, it's being popped from both. The node is taken, expanded in the order of focal. It will bring in its neighbors and populate things accordingly. Now what's important to note is in the standard sense, we use what is called a conservative window approach. So these nodes will all be expanded until they run out, until we exhaust focal, before we update the F1 min and W times F1 min, define a new window, right, and then pull those nodes into focal. So there's a few different ways, and at the end of the video I'm going to discuss alternate strategies there and their different strengths and weaknesses. But in the vanilla sense, we're just going to expand all of these 4 nodes before repopulating focal. Okay, so I think we should at this point jump across again and start to consider why we're even using focal search. Focal search is super interesting because this is the first algorithm we've had a look at that kind of lets you as the user, as the human being, choose something else that you might care about in the problem, and then also to optimize for that simultaneously. Note that I'm not saying that you're achieving the optimal solution for either one of these metrics, right? We're already getting a W times optimal solution based on the actual grid distance. And then you're also not guaranteed, right, to find the exact optimal according to F2. It's kind of this balancing act. We kind of get a little bit of the best of both worlds. So what kind of problems might you be interested in? Personally, I study pipe routing, or I did. In pipe routing, what's really, really expensive, right? You have all these pipes of these different diameters. Well, the expensive aspect of buying or constructing these pipes is actually the bends, right? So the segments that have to be bent, the 90-degree or 45-degree, custom angles as well are extremely expensive and they practically just prohibit them in construction. Well, in this sense, right, like my problem demands that I want to minimize the number of bends. If there are a bunch of solutions that are all about the same, right, I'm trying to optimize, I guess, for cost, right, the actual cost of the structural steel required to build this plant. Well, what I can do is try to find a pretty good solution. It's still like a small distance, right? The route itself is close to optimal within W times. But as well, I'm also minimizing the actual number of bends, which hopefully corresponds to this decrease in the overall cost. I could as well, of course, just use an actual cost model as our F2 as well, but that might be more complicated, but that's absolutely something that also could be exciting to explore. All of this is really just to say, though, what's important here, right, is the idea that actually, this is the first time as well, I don't have to sit down and go, try to compute, is the number of bends a consistent function? Is it an admissible function? Well, I mean, spoiler alert, it's even not, right? The beauty of focal search is we get to define our secondary f function, what we care about, really just according to us with ease, right? It doesn't matter if it's admissible or not. We're happy with anything, any solution within this window, and so that I think is kind of the beauty and the simplicity of focal search. So I'll give you another couple examples just to kind of like get your creativity flowing. Another use case for this, right, in the actual context of that MAPF and how it relates to CBS and improved state of the art there. Well, what we're going to be doing is essentially actually just tracking the number of conflicts, agent conflicts. So we're doing multi-agent pathfinding. One of the main issues and challenges in the space is that essentially all the agents want to occupy the same location at the same time. They're hitting each other, they're crashing, they're conflicting. So by rerouting agents, we can try to find better routes by ones that actually avoid hitting more and more people, right? So when they're trying to greedily plan their path, they'll prioritize the version of the path, even if it's slightly suboptimal, that avoids these conflicts, and that means we're able to kind of like more effectively search in these long horizons. The other one I think you might be actually really interested in is in the context of video games. So I heard a really cool talk from Nathan Sturdivant. He did it at one of the conferences, and he briefly talks about some of the work he did in relation to pathfinding in weighted terrains for different kind of animal mobs, right? So there are game companies out there that want, of course, different types of animals, perhaps like a deer animal versus a rabbit animal, whatever else. Maybe it's a caravan NPC. These kind of different creatures of agents, of course, should behave differently and plan their paths differently according to the actual environment around them. So one way to do this, though, is because you never want to just hard code, stay exactly on this location, right? The deer should be able to perhaps explore outside, but perhaps we want to make it preference going through regions such as a forest. Well, to do that, what we can do is simply use focal search to kind of weave in this secondary prioritization function where perhaps you do some form of count over types of terrains, weighted regions that you don't want to interact with, right? And so then you can like penalize the agent for moving through these spaces. So within some realm, they're still free. They have this flexibility, right, to go explore the quick path that runs through the field, runs across the road, things like this. But they're kind of building in these really nice behaviors that we might want from our agents. So focal search is really exciting in that sense, and it gives us so much creative freedom, right, based on the idea that we can simply now just pick any function, any criteria we want, and to kind of weave in some of that behavioral tendencies. Now, the thing I want to note in that regard is what a lot of what I'm talking about really is diving towards this idea of two-objective search. We call that bi-objective search within the field, okay? I want to cautionarily note that this is not actually a strictly bi-objective search problem. So again, focal search is just working within the bounds of this W realm over here, this little focal list. That's where we're building in these behaviors. We are not optimizing for two different objectives at the same time. We're not trying to get the optimal solution for both. That is where bi-objective search actually comes in. That is an entire realm of search, a family of algorithms in its own right. I will try to tackle bi-objective search in another video in the future. But bi-objective search is very, very difficult. It's a massive problem. Believe it or not, there's not much of a free lunch, right? If optimization for one problem was hard, two simultaneously is extremely difficult and very computationally expensive. We have these ideas entering in of this Pareto frontier, and you have to kind of like try to meet in the middle, match both optimal paths together. So that is a nightmare for a future day. Focal search is just kind of like a happy medium. That's just a unique idea working within this bounded suboptimal framework. Now, what we actually do need to talk about though is W, because we've kind of been avoiding how to choose W. So one issue with focal search is that you will need to kind of parameterize W. again, you can choose this, right, based on the suboptimality that you're happy with, which is kind of where this comes in from weighted A star and things like this. But we do have to be careful with W. So let's talk about then what happens if we chose really large W's. Well, the larger that this subsection is here, right, if it went all the way to H, essentially what happens is we start to see that a larger and larger proportion of the search space from open is actually moved into focal instead. So if focal is essentially taking up the entire list, well, again, yes, sure, we said we were okay with that suboptimality, but really we are losing more and more of the idea of even ranking nodes by effective path cost, and we essentially just move towards just ranking nodes by F2. And remember as well that that is inadmissible, and so the performance of our algorithm can also really suffer. So there is this element of having to parameterize W within what suboptimality you're okay with, but really, like, again, if focal is too small or too large, well then you kind of are not even really gaining any advantage from using focal in the first place. So that can be a little bit tricky, but you know, you're just going to try a few different values and kind of get a feel for which kind of behaviors you enjoy more. So now I want to jump across to future me here, just to go over a very brief example of what focal search will actually look like in a real problem and demonstrate this effect in a worked example. Okay, so that was focal search, but the last thing we have to talk about is still the idea of how we choose our window strategy, how we choose this window here between F1 min and W times F1 min, and when we repopulate this, when we recalculate this as part of the search itself. So I began by discussing the idea that here, when we exhaust the entire focal before we recompute this is called the conservative window strategy, which maybe is like the base vanilla implementation of focal search. There's this other aspect to the problem though. So there is another version of this that we might care about, which is called the sliding window strategy. So imagine instead this time, as we start expanding nodes out from focal, and of course they're also being removed from open, well, why don't we continue to track the F1 value that remains in open, and as we get rid of nodes, right, so we expand B, yeah, maybe then we expand A, well, all of a sudden, well, we note that the F1 min is now actually updated to a new value. So we can do this in this sliding window approach. What we will do is we'll actually recompute our window immediately. We will do a linear scan through open to essentially shift our WF min to wherever it should be, and then we will take the new nodes, right, so this would be our EFG, and we would then bring them in to populate the focal queue. So this has strong advantages, particularly if the G, for example, here, was actually the goal, right? So what we see is that in these kind of cases, what we could very much be bringing in, because we're populating the list earlier and earlier, well, we may bring in actual goal nodes and we'll be able to find them far sooner instead of having to exhaust the CD perhaps. So there can absolutely be situations where the G begins ranked right at the front and then the EF populates thereafter. So essentially, it just means that the sliding window strategy is able to potentially find the goal faster, terminate search faster, as well as the idea that realistically, right, we're kind of, if you're okay with that suboptimality sliding, it just means that we get to explore more nodes, we have more in focal to choose from, which means you can kind of build in more of this additional optimization according to the secondary F function. So essentially though, of course this comes with additional downsides. Primarily, right, we're doing this extra bookkeeping. So we have to maintain, we have to keep checking if the F1 min updates. And then of course, as part of that, we have to do this linear walk, this linear scan through the open list to continue to populate, to draw in nodes, and then put them into focal. There is this other aspect as well, as we're essentially increasing the number of heap operations that we're also doing, right? They have to be moved, we're gonna have to use them, of course, in focal according to their new ranking. And so we have all of these additional operations and things that may actually detract from the overall performance of search. And then I think there's the idea as well that we might be accepting slightly worse solutions, right? It could be within this W initially, but as we slide it, well, we're essentially allowing slightly worse solutions overall. So depending on what you care on, you can kind of choose which kind of window strategy you might like. The conservative one is really nice and easy to implement, but I think that the sliding window one does have some significant advantages in terms of better control over behavior, faster population of nodes that could be important, right? And could, of course, also be the goal and lead to terminating sooner as well. So anyway, this has been Focal Search. I think it's a really exciting algorithm. We are going to revisit all of these ideas soon within the context of CBS and ECBS, enhancing conflict-based search. Thank you so much for watching, and please join me in the next video where we do talk about ECBS. Thanks.